All right, everybody. Thanks again for continuing virtually. Hopefully, it is the last week. Oh no, Zoom on my computer is having a trouble recording. Try this again. All right, see if this works. Yeah, so just saying thank you again for signing on again virtually. Hopefully this is the last class and we're back to in person next week. And anyone who's comfortable, please turn on your camera just so I can see that there's someone out there. Cool. So last class, we started studying zero-sum games. And we saw a few ways in which they were special. In particular, we thought they had a value, which sort of meant the order of play didn't matter, right? Like we could think about my opponent moving first and me best responding, which would normally be an advantage. Or we could think about me moving first and my opponent best responding, which would normally be a disadvantage. But in zero-sum games, we showed the min-max theorem, and sort of what that means at a high level is that the order of play didn't matter. Let's see, I'm hearing somebody. Let's try to make sure everyone's muted this year. That's Insha. All right, I'm gonna mute you, Insha. All right. And a consequence of this was that in two-player zero-sum games, at least, and we're going to sort of think this class about how important this two-player caveat is. In two-player zero-sum games, a consequence of this is that, at least conceptually, equilibria could be computed easily. Like normally in a game, if I want to think about what an equilibrium is, I need to engage in some kind of counter speculation. I need to think about what my opponent is going to do, and what I should do depends on what they're going to do, and vice versa. There's sort of a kind of circularity because it's an equilibrium of a simultaneous move game. But for zero-sum games, since order of play doesn't matter, I can think about this sequence of moves where I move first, and then my opponent best responds. And I can just sort of use this backwards induction kind of reasoning to sort of think, okay, like, what are they going to do in response to what I play, and taking into account what they're going to do, what should I do? So sort of a linear kind of reasoning you could use, and we went through an example of this to figure out how to find the equilibria of a two-player zero-sum game. Right, you only need to think about these sort of min-max strategies. But like in our example in which we actually like concretely computed equilibria in like a toy zero-sum game, like we had the game matrix in front of us, right? Like we had this presidential election game, and like we had all the numbers in front of us, and we did like careful calculations. We had to like write out equations in terms of the payoffs in the game matrix, and think about, okay, well, what exactly is my opponent's expected utility if I play this mixed strategy? It's the kind of thing you couldn't really do if you didn't know the game matrix. And so what I want to think about today is whether there is a computationally plausible story, sort of analogous to sort of the story we told around best response dynamics in congestion games, that tells us how we might find Nash equilibria in like large zero-sum games. Is there some dynamic such that, number one, it's a plausible dynamic. It's a good idea for people to play according to this dynamic. And number two, like sort of inevitably leads to Nash equilibria in multiplayer zero-sum games, sort of in the same kind of way that best response dynamics inevitably led to equilibria in congestion games. So that's like the main question I want to think about today. And the first thing I want to think about is to what extent like everything we've talked about for zero-sum games like really hinges on the two-player caveat. Because it would sort of be a bummer if we could only talk about two-player games. Like, like maybe some things we can describe as two-player zero-sum games, but there's just like a limit to like the size and scale of an interaction you can describe if there's only two players. Okay, so the first question I want to ask, do any of the special properties we've sort of discovered so far for two-player zero-sum games carry over to n-player zero-sum games? And like it certainly makes sense to like define such games. Like I can define an n-player zero-sum game. It's just an n-player game such that for every possible action profile, for every possible state of the game, if I sum up over the utility functions for each of the n players, they sum to 0. Okay. So first of all, what do people think? Like, are n players 0? Like, is the fact that I've specified that a game is zero sum, does that tell you anything interesting about an n player game, the way it does about a two-player game? Feel free to unmute and share your beliefs.
It seems like now we no longer have that property where we can like reduce it to just one value with the min-max. Now we can only like reduce it to, I think, n-1 values.
Yeah. So like, okay, so I'm going to claim that the answer is no in some generality. And I'll claim the following like meta theorem, and I call it a meta theorem and put scare quotes around it because this isn't exactly a formal statement, but I think you'll sort of see in the meta proof what I mean. So I claim that n-player zero-sum games don't have any special properties at all that n-1 player general games don't have. Okay, so like this kind of statement still allows two-player zero-sum games to have special properties because, if n is 2, an n-1 player game is a one-player game. It's not even a game. Of course, it's got lots of special properties. But this is saying like, look, if we're talking about, like a 216-player zero-sum game, like there's nothing interesting that is true about it that isn't also true about a 215-player arbitrary game. Okay, so to the extent that like the word zero sum is telling us anything at all, nothing can possibly be true about an n-player zero-sum game that isn't also true of a completely arbitrary game with one fewer players. Okay, and so like in particular, like we shouldn't expect that zero-sum games, when we have more than two players, should have like a minimax theorem, like, order of play should probably matter. We shouldn't expect there to be any like easy way to compute equilibria in these games. Unless there's a plausible dynamic that converges to equilibrium in all games, we shouldn't expect in general there to be any dynamic that's like special to like n-player zero-sum games. And does anyone want to like venture a guess as to what the meta proof is of this meta theorem? Like maybe you want to think about it the other way around. Like suppose I had a completely arbitrary n-1 player game. How could I turn it into an n-player zero-sum game in a way that wouldn't change any of the like essential properties of the game.
Is it just to add a player that has a negative utility to the total utility or something?
Exactly. Yeah. So like, let's say I've got an n-1 player game. It can be completely arbitrary, so there's nothing special about it. I can just turn it into an n-player zero-sum game, like syntactically. I'm going to add a new player n who's like irrelevant to the game. Like he has no choices to make. He's only got like one action, so he's got no choices to make. He's completely payoff irrelevant to the other players. Like he does the same thing no matter what. So like, the other players, their utilities aren't changed at any game state by the fact that I added this player, right? So the equilibrium structure is exactly the same as it was before in the n-1 player game. Like this new dummy player I added really like is not a participant in this game. He doesn't change the utilities. He doesn't even have any choices to make. It's only like a syntactic modification that I've added this new player. And I can, since he's not participating in the game, he's only got one action. I can define his utility to be anything I want. It's not going to affect the equilibrium structure of the game. So why don't I just define his utility to be the negative sum of all of the utilities of all the other players in the game? Okay, so now like by fiat, this is a zero-sum game. Like I've just defined this new dummy player to have utility exactly the negative of everyone else's. So everything now sums to zero, but I haven't changed the game in any actual way. Like this was purely a syntactic change. And I just, I moved it from an n-1 player game to an n player game. Okay, so like, this is why we shouldn't expect zero-sum games to really have any structure we can take advantage of, except in the special case of two-player zero-sum games, right? For like two-player zero-sum games, like are still special and are allowed to be special by this meta theorem because one-player games are really very different than two-player games. Okay, so questions about this? Like, for a two-player, I guess the point is, for a two-player game, if I tell you it's zero-sum, that tells you something sort of structurally very important about the game. Okay, like we proved some of those important things last class, like the min-max theorem. But if there's more than two players, if someone tells you the game is zero-sum, like by itself, that is entirely meaningless. It has no structural implications at all for, cooperation or, order of play or equilibrium or anything else. Like any game could be made into a zero-sum game if you can, add a player. So like if someone tells you something is a zero-sum game, they haven't told you anything at all unless they've also told you something else about the game. Okay. So like nevertheless, that doesn't mean that there's no interesting subclass of zero-sum games that sort of generalize two-player zero-sum games. It just means that in order to specify an interesting structured class of games, I need to tell you something other than that it's zero-sum. Okay. So in particular, like I'm going to define a class of games here that when these games are also zero-sum, share lots of the structure of two-player zero-sum games, except these are n-player games. And I'm going to call these separable graphical games, although, we'll talk through what they mean. Like the graphical part is maybe like a red herring, because this will make more sense when we define it, but like the graph could always be like a complete graph. It's really the separable part that is important here. Okay, so let me tell you what is a separable graphical game. It's like, first of all, underlying this thing is a graph. Think about the vertices as being the players. Okay, so this is going to be like an n-player game. There's one vertex for every player. And think about the edges. There are edges between players that are payoff relevant to one another. So it might be that your action doesn't actually change, it doesn't actually like affect my utility in the game at all. Like maybe it's a, like a, yeah, you could define, you can imagine games where like, for some of the players just basically don't interact with me, they interact with like other people. And so some players might be payoff irrelevant to me. There would be no edge between me and those players in a graphical game. Some players might be payoff relevant. There would be an edge between me and the player. There's nothing here that's saying that the graph can't be a complete graph, in which case potentially everyone is payoff relevant to everyone else. But what's sort of more important is the separable part of the game. And so like what it means that the game is separable is that really what's happening is I'm playing simultaneously a bunch of two-player games, one with each of the, one with each of my, opponents in the game. And when I want to figure out what my utility is, I sort of sum up my utility over these two-player games. Okay, now I'm not playing them independently. Like I can't pick like a different action for each of my opponents. I have to pick like one action, but like that action is sort of used in all of the two-player games I'm playing simultaneously. Okay, so like in particular, the way like that manifests itself in the definition is that if I'm looking at the utility function for player I can write that as the sum over all of the other players j that are payoff relevant to him. It's the sum over all of the other players that he has an edge to in this graph of some utility function that might be specific to that pair, right? Like I might have a different utility function, for Alice, and a different one for Bob, and a different one for Carol. But like I can evaluate, given the action that I chose, AI, and the action that player J chose, AJ, I can evaluate what my sort of utility is in this little two-player interaction that we've got between player I and player J. And my cumulative utility is just the sum of all of these pairwise utilities with each of the other players in the game. Okay, so does that make sense? It's sort of like in a separable game like this, sort of like everyone is simultaneously playing a bunch of two-player games with their opponents, their neighbors in this graph. They've just got to like pick like one action to use simultaneously in all of these two-player games. Go ahead, Sarah. And you don't need to raise your hand, by the way. You can just like shout out.
Okay. I was just wondering if you could explain again what the edges represent.
Yeah, so the edges, like if the edges are confusing, you can like imagine that everyone's interacting with everybody. But like more generally, the edges represent who in this game is payoff relevant to you, who you're interacting with. Like it might be that there's, people in distant corners of the world that just don't have any direct effect on your utility at all. Right, so like in a congestion game, like a traffic routing game, like in principle, like the United States is all on one road network. But like if I'm commuting in the morning to Penn and someone in New York is commuting in the morning from New Jersey to Columbia, our routes, like the set of routes we can take just don't share any roads. And so they're not directly payoff relevant to me. They might indirectly affect my utility because there might be a chain of people that sort of are affected, beginning with this one person ending with me. And so they're relevant for like what is done in equilibrium, but they're not directly payoff relevant in that their actions don't directly change my utility function. And so if we were to describe that as a graphical game, there would be no edge between me and them.
Oh, so when we're talking about like the proof for the when you add in the new player and with the trivial action set, technically he would be like an isolated node because he wouldn't affect anybody's payoff.
Yeah, like if I were adding in a dummy player, they wouldn't have edges to anybody.
Okay, thank you.
But like the reason I say the graph here is like a little bit of a red herring and you shouldn't like get caught up in it is like you could always imagine it's a complete graph, like everyone's interacting with everybody. yeah, that's only like more general. The important part, the important part is not the graph. The important part is the fact that yeah, if there were no graph, I would just write this as the sum over all of the other players. The important part is that everyone's utility can be decomposed as the sum of the utility they get from interacting with each of the other players in the game. Okay, does that make sense? Okay, but okay, just to draw like the graph, you haven't seen one before. Right, there's these vertices, and maybe the graph looks like this, meaning player B and D are directly payoff relevant to player A, but player C is not. If player C changes their action, it doesn't directly affect the utility for player A. That doesn't mean that they're not relevant in the game. Like the fact that C is here, since C interacts with B and D, affects what B and D do, and what B and D do affect what A does. So the fact that C is here might be important to the equilibrium structure of the game. It just means that they're not directly payoff relevant. That's sort of the kind of structure that the graph is capturing. But, like I could, without loss of generality, it could always be like a complete graph, and these utility functions could be 0, like the utility functions on the edges I just added. So like the graph is like not adding much. The fact that I can, like the important part is the fact that I can decompose the utilities across the edges. Okay, and so that's some class of games, right? Like separable games. What I want to think about are, so separable games, they can have a lot of players, right? They can be like n-player games. What I want to think about are separable zero-sum games. Okay, so I'm going to think about n-player zero-sum games. And I know more than that they're zero-sum, right? I know that, like, if I only told you an n-player game was zero-sum, that wouldn't tell you anything interesting about the game. But I claim if I tell you both that the game is zero-sum and that it's separable, okay, then it tells you something interesting about the game, and it'll have many of the properties of two-player zero-sum games. And note in particular that like a two-player zero-sum game is a special case of an n-player separable zero-sum game. It's just the graph just looks like that. There's only 2 players. Okay, so it's sort of like the degenerate case, but like this is a class of games that is like just strictly more general than 2-player zero-sum games. And so in particular, the claim is that there's still going to be like a minimax theorem for these 2-player zero-sum games, for these n-player separable zero-sum games. Like they'll still have a value. Every equilibrium will have the same payoff for each player. They're easy to compute, these equilibria, and in fact, not just like with an algorithm on your computer. Like we're going to show that there's sort of an efficient dynamic that naturally converges to equilibria in these separable zero-sum games, even with n players. In particular, this will give us a dynamic for 2-player zero-sum games as a special case. And note, like, right, these separable games, like the utility functions, are written as sums of like utility functions for like 2-player games, one that you're playing against each of your opponents. When I say that a separable game is also zero-sum, that does not necessarily mean that each of these constituent 2-player games is zero-sum. Like it could, but that would be stronger than what we're assuming. Like the only thing we're assuming is that in aggregate, the game is zero-sum. If I sum over the utilities of all n of the players at any game state, I get 0. It doesn't mean that the utility of me and someone across the edge from me on some particular one of these 2-player interactions is zero-sum. There might be gains from cooperating locally. It's just that there aren't globally. Okay. So that's sort of the setup for what we're going to do, the class of games we're going to study, and roughly what our goal is to show that there's like going to be an efficient dynamic that converges to equilibria in these games. Next, we're going to execute on this plan. But before we do, are there questions? So the class of games is clear. Okay. So, okay. So as like a spoiler, right? It's like one instance of the dynamic, the class of dynamics that we're going to show converge to equilibria are everyone playing according to the polynomial weights algorithm. Okay, so we could say, like we're just going to study what happens when everyone plays according to the polynomial weights algorithm. But although the polynomial weights algorithm is a very good thing, very good idea to play if you're playing in a zero-sum game, it's a very specific thing to do. Like, to the extent that we can, if we say if everyone plays according to the polynomial weights algorithm, play converges to Nash equilibrium, that's true, but it's a very narrow statement. Our goal, just as it was in best response dynamics, is to sort of define a whole class of dynamics such that if you play according to anything in that class, you converge to Nash equilibrium. So in best response dynamics, that sort of came from leaving all sorts of things underspecified in the algorithm, like the order in which players move, the specific better responses they take, right? Sort of those things didn't matter. You could fill in those details however you wanted. And we showed that better response dynamics converge to equilibrium. So here, what I'm going to do is I'm going to define a, like suppose people play according to some dynamic over T rounds, right? So they generate a sequence of T action profiles. I want to define like some property that this playout sequence might or might not have. And we'll show that if the playout sequence has this property I'm defining, then play must have converged to equilibria. And in particular, if everyone plays according to the polynomial weights algorithm, the sequence will have this property, but there's other ways to get it too. Okay, so suppose we have a sequence of action profiles. Imagine that this results from just sort of the realized sequence of actions that everyone plays if they sit down and play this game, for T rounds. Okay, so remember, an action profile is like a vector specifying what each of the n players does at each of the time steps. So we'll say that such a sequence of action profiles has regret delta of t if simultaneously for every player I and simultaneously for every action AI star that they might wish they had played, they might think about playing and sort of regret as they go to sleep at night, that if I look at player I's average utility averaged over time for the actual sequence of action profiles that was actually realized, that this is at least as high as the utility they would have obtained in this counterfactual world where everyone else continued playing as they actually did in this sequence of action profiles, but player I did something different. Player I instead, every single round played this action AI star. Okay, so this is saying like, right, player I has regret delta of t if they could have done better by playing action AI star every round instead of what they actually did. And the amount they could have done better by was delta of t. And they have regretted most delta of t if for every alternative action they could have considered consistently playing every single day, instead of what they actually did, they couldn't have improved their counterfactual payoff except by delta of t. Okay, and if this action sequence has the property that delta of t gets smaller and smaller as t gets bigger and bigger, if their regret goes to 0 as we play for longer and longer, we'll say that this action sequence is no regret. Okay, so let me like pause here because this is sort of an important definition, but I think the terminology is sort of evocative. Like on the left, we have what player, the action sequence that was actually realized. On the right, we have this counterfactual world where everyone else, except for player I, did what they actually did. But like player I is now imagining what would have happened if instead he had done something different and played AI star instead. And if he could have done something better in this counterfactual world, we say that he has regret. He regrets not having done that instead. And delta of t is the amount by which he could have done better. And if that amount is almost nothing, if it's going to 0, we say he has no regret. Okay, and the sequence has regret delta of t, or the sequence is no regret if this is simultaneously true for every single one of the players. So are there questions about this?
So just to clarify, each player is wondering whether there was a single action they could have played throughout the T rounds that would have made them better off.
Exactly. So they're not comparing to like this much stronger thing of playing what would have been the best response separately at every round, right? Like if I play a rock, paper, scissors tournament, it's not that I'm kicking myself at the end thinking like, oh, at like, round 16, you played scissors. So like, I really regret not playing rock then. And then like at round 17, you played paper. So I really regret not playing scissors. Or right? Like if I was comparing myself to that, like no matter what, I would like always have like enormous crushing regret. But I'm saying, look, like if I ended up winning like less than a third of the time, then like in hindsight, I could have done better by like playing rock every time or paper or scissors. Then I will have regret. Does that make sense?
Yeah, understood. Thank you.
Yeah.
Can you explain the definition again of no regret and what the T means?
Yeah. So let's think about, let's maybe break it down. So let's think about what does it mean if I regret not having played some particular action AI star every day instead of the sequence of actions I actually played. What it means is that if after everything is said and done, like the action profiles in the sequence are actually realized, if I could have done better in hindsight by just playing the same fixed action every day, AI star, instead of what I actually did, which was potentially playing something different at every round, then I say I have regret to action AI star. And I can quantify how much that regret is by asking how much better could I have done if I had played AI star every round. And we say that I have regret delta of t if I have regret at most delta of t for every other action I could have played. And we say that the sequence of actions has regret delta of t if every player has regret at most delta of t for each of the other actions they could have played. Does that make sense?
Yep, thank you.
I have a question as to why we're able to assume that each player is going to keep playing the same move. Like, I guess like in the rock, paper, scissors example, like if you started playing rock every turn, it just kind of like in like a real world application, like isn't there definitely a big difference if you're just doing the same move every time?
Oh, so we're not assuming anything of the sort, right? So like the actual sequence of action profiles, A1 through AT, this is arbitrary. Like presumably the players are playing different actions every single time. The question is just like, what is the benchmark they are comparing themselves to in, when we're saying what they regret? And you're right, you could compare to a stronger benchmark. You could say, okay, like, did you do as well as the best possible sequence of moves you could have played in hindsight? But that's not a very useful benchmark. And you can sort of realize why by thinking about rock, paper, scissors. Like, if I'm comparing myself in themselves in hindsight to the best possible sequence of actions. But once I know what actually happened, there's always a sequence of actions that would have caused me to win every time. So if that's how I was defining regret, there's just no possible way I could behave in this game that would cause me to have low regret. So regret here is defined with respect to a much weaker benchmark of just doing a single thing consistently, right? Like you can have low regret while playing some complicated, algorithm that causes you to play different actions on different days. It just means that you're doing better than you could have done in hindsight by playing something consistently. Does that make sense?
Yeah, this makes sense. Yeah.
And what is the notation one more time of the OT of 1?
Oh, this just means that little o of 1 means, a function that like goes to 0. And the subscript t here means t is the variable. So as t gets big, as t goes to infinity, delta of t goes to 0. Okay. And by the way, like, I'm not making any normative claims about whether, like as you arrange your life and your, like, you lay out on your deathbed your wins and losses and the things you regret, that somehow you should compare yourself only to benchmarks of like, fixed actions. Like, instead, like, we're going to prove things about sequences of play that have this property. And the reason that is an interesting thing to do is because we know how to generate sequences of play that have this property. Like in particular, right? Like for a particular player I, this is exactly the form of the guarantee that polynomial weights promises them if they play the game with polynomial weights, no matter what their opponents do. Right? Like for you as a particular player I, if you decide to play this game with polynomial weights, it will promise you exactly this, right? You will do as well as the best fixed action in hindsight. That's making no assumption about what the other players do. They could be doing anything. And so in particular, if everyone plays according to polynomial weights, everyone will have this guarantee simultaneously. So if we just simulate play of this game in which all n players play with the polynomial weights algorithm, we've proven that it will generate a sequence of play that has this no regret property. And in particular, for polynomial weights, this function delta of t will go to 0 at this rate that we proved, 1 over square root of t. Okay, so this is not some definition that, like I'm just pulling out of a hat and like it's not clear how to satisfy it. We know exactly how to generate sequences like this. They will be generated by, this will just be like how play turns out if everyone's playing according to the polynomial weights algorithm. But it's not the only way. Like there's other algorithms that guarantee diminishing regret. There's things you could do that might not even guarantee diminishing regret in the worst case, but happen to lead to diminishing regret when you play them. It's a sensible thing to expect to happen, because if you are playing in such a way that causes you to have high regret, it's pretty easy for you to switch to a different algorithm that causes you to have low regret. You could, for example, start playing the polynomial weights algorithm. And it's not hard to play the polynomial weights algorithm. It's a very simple algorithm. And so it's not crazy to think that observed sequences of play should have low regret, since there are simple, sensible ways for players to obtain it. Okay. But I guess the point is, like, the reason we're not talking specifically about the polynomial weights algorithm, but instead sequences that have low regret, is this is a more general family of dynamics. Any play dynamic that ends up resulting in a sequence that has low regret will have the properties that we prove about sequences that have low regret. Okay. So I want to think about play dynamics now, and I want to introduce some notation. So suppose we have a sequence, suppose we've played out some game, some n player game for t rounds, and I have this sequence of action profiles, A1 through AT. I want to write AI bar. Oh, so like for some particular player I, there's like a sequence of actions they've played over these T rounds. Like they played AI1 at the first round, then AI2, all the way up through AIT. Right, so a sequence of action profiles encodes in particular like a sequence of T actions for each player I. And I want to write AI bar for the mixed strategy that just corresponds to picking an action uniformly at random from this sequence. Okay, so like the sequence of action profiles specifies a sequence of T actions for each of the players. AI bar is just like the mixed strategy that corresponds to uniformly randomizing among those T actions. Okay. And so with that notation in mind, this is the theorem I want to prove. I'm going to say, look, consider any zero-sum separable game, n players. And imagine that it's been played by some, people are using like whatever algorithms they want to play this game. They're just playing the game. It's been played out to T rounds. So we have a sequence of T action profiles. Let's suppose it happens that this sequence of T action profiles has regret delta of T through whatever means. Maybe everyone was playing with the polynomial weights algorithm, in which case we know exactly how small delta of T is. It goes to 0 at a rate of 1 over root T. Maybe they did something else and it just happened to have low regret, whatever. We've got a sequence of action profiles that has low regret. Then, if I look at the following collection of mixed strategies, one for each player. For each player I is just playing the strategy AI bar, which just means randomizing uniformly among the actions they played in this particular sequence of action profiles. Then this vector of mixed strategies, one for each player, is actually an approximate Nash equilibrium. And how close we are to Nash equilibrium depends on how small the regret is. An n times delta of T approximate Nash equilibrium. And so, like for example, if we were playing with the polynomial weights algorithm, like delta of T would be going to 0 at a rate of 1 over root T. Right. So, we could ask, right? Suppose delta of T is the regret bound we get from the polynomial weights algorithm, which remember is just 2 root log K over T. We could ask, like, okay, like given this theorem, how long do we need to play before like play has converged to an epsilon approximate Nash equilibrium? And we could solve and we could just answer that question. It would be something on the order of n squared, the number of players squared, log K many rounds, over epsilon squared. Okay, so something pretty fast. Sort of the rate of convergence depends quadratically on the number of players and on the inverse of how close you want to get to approximate Nash equilibrium, and only logarithmically in the number of actions in the game. And in a 2-player game, where n is just 2, this says, look, we actually converge to an epsilon approximate Nash equilibrium, not just in a number of steps that is like polynomial in the number of actions, but in a number of steps that is only logarithmic in the number of actions. Like it could be a really big game, really big 2-player game, say. The convergence is sort of exponentially fast in the number of actions. Okay, so this is what I want to prove. That if people play in a zero-sum game, not just a 2-player zero-sum game, but an n-player zero-sum game, as long as it has this separability property, then play in this averaged sense converges very quickly to approximate Nash equilibrium. Okay, and it's not just actually that they have to play with polynomial weights. The only thing that matters is the regret of the sequence. So any way they get there converges to equilibrium. Okay. So
And what is an approximate Nash?
Right. So remember, an approximate Nash, or an exact Nash equilibrium, is a collection of strategies, one for each player, so that nobody can gain at all by deviating. Nobody can increase their utility by even a tiny little amount. An epsilon approximate Nash equilibrium is a vector of strategies, one for each player, so that maybe there's somebody who can gain by epsilon by deviating, but not by more than that. So nobody can improve their utility by more than epsilon by deviating. Other questions? Okay. Okay, so let's prove this in little bite-sized chunks. And so I want to start with sort of like a useful, basically just syntactic fact, but something that we're gonna use a couple of times. So I want to just, make sure we all understand it. So let's consider for some particular player I, and for some particular fixed action, AI star, that they might consider playing. This expression here, which is just cumulatively over time, what would have been their average payoff if all of the other players played according to the action profile at day t, but player I consistently played this one action AI star every day? Okay, that's what this expression on the left is. It's just sort of saying, okay, we're averaging over time of the utility of player I, except it's not the actual utility of player I, because instead of having player I do at day t what player I actually did at day t, we're having player I play this one fixed action AI star, while in the meantime, everyone else is playing, as they actually did at day t. So this is sort of like the counterfactual utility player I would have gotten in a world in which he deviated to consistently play this one fixed action AI star every day. Okay, that's just that's what this thing is here. And I just want to note that, okay, it's written like this, but I could swap the order of these summations. That doesn't matter. I could bring this, instead of averaging at the outside, having this 1 over t out here, I could bring the 1 over t to the inside. And if I did that, then what I would get here would look like an expectation. Right? What is this expectation? Now we're looking at the particular two-player interaction that player I has with player J, because remember, this is a separable game. And we're saying, okay, what is player I's expected utility if he plays AI star and player J uniformly randomizes across all of the actions, AJ1 up through AJT, right? Putting weight 1 over t on each of them. So we're just sort of syntactically realizing that the sum over t actions, putting 1 over t, weight 1 over t on each of them, this is just the same thing as an expectation of selecting one of those t actions uniformly at random. Okay, and so the upshot is just, and this is again entirely syntactic, but the upshot is just that if I'm looking at this quantity on the left, which is just sort of player I looking back over his life and sort of wondering how would have things been different if I had played AI star every day, that's exactly the same thing as him wondering how well off would I be if I played AI star today and my opponent, all of my opponents randomized uniformly according to this mixed strategy that we call AJ bar, which is just randomizing uniformly at random between all of the actions they historically played. Okay, so there's nothing going on here. It's just, averaging over the t days is the same thing as taking an expectation over a uniform distribution over the t days. Okay, but is this clear? Well, in some sense, there's nothing going on here. It's just a syntactic transformation. On the other hand, it's going to be quite useful to think about this counterfactual quantity. How well would I have done, now that I'm looking back on the years of my life if I had just played this one fixed action every day, and viewing that as sort of my responding to a mixed strategy with an action. So is that clear?
Are we assuming that your opponent over the T days is already selecting like from their actions uniformly?
So our opponents did whatever they did, right? Like at this point, everything's fixed. We're looking back over the T days. So, you know, each of our opponents, J, played some particular action, AJT, at each day. Okay.
Yep.
And we're just saying, well, now, you know, now that we're here looking back, we know exactly what they did. The average payoff we would have gotten for playing AI star every day. That's just another way of saying what payoff would we get if we played AI star against opponents who were uniformly randomly choosing actions according to this history. Make sense?
Yeah.
Cool. Okay. So remember, like, what do we want to prove? We want to prove that if everybody were playing according to this mixed strategy, AJ bar, that this would actually be a Nash equilibrium, or at least an approximate Nash equilibrium. And what that means is that we wouldn't be able to, no player would be able to gain much by deviating from this mixed strategy. And what would they deviate to? Well, like, of course they would, the thing that would, you know, gain them the most is if they deviated to their best response, given the, you know, equilibrium strategies of their opponents. Okay, so let's give a name to that best response. Let's imagine that every player is playing according to, every player I is playing according to this mixed strategy AI bar. Okay, like we want to claim that this thing is an approximate equilibrium. So let's say that if everyone's doing that, you know, okay, something will be a best response for player I. Let's just call that thing AI star. AI star is just a best response of player I to the mixed strategies of his opponents when they're all playing AJ bar. Okay. And one obvious thing I want to note is that if I look at the utility for player I, when he plays AI star, his best response to his opponents, and all of his opponents play AJ bar, they're part of this purported equilibrium, that of course, you know, player I's utility in this case can only be higher than if instead of playing his best response, he did something else, AI bar, his part of the equilibrium. Because by definition, like what it means for AI star to be a best response is that his utility is higher when he does this than when he does anything else. Okay, so if everyone's playing according to their part of the sort of purported equilibrium, where everyone's playing AJ bar, and any player I deviates to play his best response, AI star, that can only increase his utility, can't decrease it, because that's what a best response means. Okay. So far we've sort of said, you know, like basic things that have nothing in particular to do with the premise of the theorem, right? Like this first thing was, you know, like just noticing that averaging over T rounds is the same thing as taking an expectation over a random distribution on T things. The second thing was kind of just the definition of best response. Let's now start, you know, actually using the hypotheses of the theorem. So like the one thing we know, right, the one thing we have to work with is that the sequence of actions that we're starting with, the sequence of action profiles, has delta of T regret. Okay, so let's like start by just unwrapping what that means. Well, it means that for every player I, if I look at the utility that that player gets on average over this sequence of T action profiles, it is at least the utility that they could have gotten counterfactually if they had played any particular action AI star. In particular, we might as well choose the AI star that is the best response to the AJ bar strategies of their opponents. and everybody else played according to this mixed strategy AJ bar. Right? And just note it in writing down this right-hand side, I'm using our first observation here, right? Like what polynomial weights actually says, like the polynomial weights theorem, like verbatim, says that your average utility over time is at least your average utility of playing any fixed action over time. And here we're using this observation that your average utility over time of playing any fixed action is actually just your utility of playing that fixed action against opponents who are playing mixed strategies that are randomizing across those actions. Okay, so this is just the promise of it was just the meaning of the regret guarantee together with our first observation before. Okay, so we have this guarantee for every single one of the players. I've written it down for like some particular player, player I, but the fact that the sequence has delta of t regret tells us that this is true for all of the players I. Okay, so we've got this like inequality, one for each of the players, and they're all true. And so it is very tempting at this point, if you have a bunch of inequalities that are all true, to like sum them up, because the sum of the inequalities will also be true. Okay, so let's do that separately on the left-hand side and the right-hand side. I'll sum up the left-hand side over all of the players, and I'll sum up the right-hand side over all of the players. And since all of these inequalities are true, I'll also know that the sum of the left-hand side over all of the players is at least the sum of the right-hand side over all of the players. Okay, so here's the first little bit of magic. Right, so I've got the inequality here. This is the upper inequality. This is for a particular player I. What I'm doing now is I'm inserting into it a sum over all of the players I. So now we're summing up over all of the players. Okay. And I claim that it sums out to 0. Can anyone tell me why?
It's zero sum.
It's a zero-sum game, right? So what do we know about zero-sum games? At every action profile, if we sum over the utilities of all of the players, it comes out to 0. Now, here, we're summing over t action profiles, but that's okay. Like, for every action profile, meaning for each day t, we have a sum over all of the players. And at that action profile, because it's a zero-sum game, the sum of the utilities of all of the players at that fixed action profile has to be 0. And so we're just summing up over t terms, each of which are 0, and so we get 0. Okay. So like the left-hand side of this inequality, when we sum it up over all of the players, like greatly simplifies. It's just 0. And this is because it's a zero-sum game. Okay, is that clear? So we've written out an inequality that comes from our regret hypothesis. We've summed up over the left-hand side of this inequality, and we've used the hypothesis that our game is zero-sum. Okay, how about the right-hand side? So let's sum up over the right-hand side as well. Well, nothing immediately magic happens on the right-hand side. Like I've got the right-hand side. I can sum up over all of the players. But on the right-hand side, like this doesn't equal 0 when I sum up over all of the players. Can anyone tell me why? Like how come this expression here doesn't equal 0, even though even though it's a zero-sum game and I'm summing up over utilities over all of the players?
Is it because this is a mixed strategy, so it's an expected utility?
No, just because we're talking about
Is it
mixed
because we're not
strategies.
requiring that they're individually zero sum?
No. So what does it mean that a game is zero sum? It means that at every fixed action profile, if I sum up over the utilities of the players, I get 0. That's what was happening here, right? Like we have a fixed action profile. Each player J is playing AJT, and we're just summing up over all of the players. Here, something different and sneakier is happening, because these are sort of like counterfactuals, right? So it's not that everyone's playing a fixed action profile. When we consider the term that corresponds to player I, we think of what happens when player I deviates to play this best response, AI star, whereas all of the other players, J, continue playing AJ bar. But when we consider the term corresponding to the utility for player J, player I isn't playing AI star anymore. Player I is playing AI bar. So we're summing up over all of the players, but in every term, we're evaluating player I's utility in this counterfactual world where it is player I who deviates. So every term in the sum is actually the utility of player I at a different action profile. Okay, and so we don't know anything about how these, like, what zero sumness tells us is if we sum up the utilities over all of the players at a fixed action profile, we get 0. But that's not what we're doing here. We're summing up over all of the players of their utility in a different action profile, the one that results if they are the ones who deviate to playing their best response. Does that make sense? But okay. So we've got the sum of the right-hand side is, this thing, but the sum of the left-hand side is 0. Okay, so we can rewrite this, since we know the left-hand side is bigger than the right-hand side, we can rewrite this as n times delta of t, n times this regret term is at least the sum over all of the players of their utility when they are the one who deviate to their best response. Like when for each player I, we're looking at player I's utility when player I deviates to playing his best response, and all of his opponents are playing according to this mixed strategy that is supposedly, an approximate Nash equilibrium. Okay, we know that the sum of the gains by deviating cannot be more than n times delta of t. Okay, another trick. So these terms here, right? Remember, for each player I, we're taking their utility over a different action profile, the action profile where they deviate to AI star, but everyone else plays according to their part of this approximate Nash equilibrium, AJ bar. I'm going to subtract off a term for every player. For every player, I'm going to subtract off a term equal to their utility if they don't deviate. Okay, so we've got the utility for player I if they deviate to playing their best response, minus the utility for player I if they don't deviate to playing their best response. They just play according to AI bar, their fixed mixed strategy that is part of this thing that we're trying to show is an approximate Nash equilibrium. Okay, so we had like this expression up here, and then down here, I subtracted off a term, inside each term of this outer sum, and I'm claiming these two things are equal. Can anyone tell me why that's true?
The second term is it follows the zero sum game rule, so it goes to 0. It's equal to 0.
Yeah, so it's again because this is a zero sum game, and now we're summing up over all of the players of their utility at a fixed action profile. Like everyone in every one of these terms is playing according to their fixed mixed strategy AI bar. They're not deviating differently in different terms. So this thing here, term by term, it might take different values, but in aggregate, when we sum up over all of the n players, this thing just adds out to 0. And so it doesn't change the value of the whole sum. Okay, so we're using, again, the fact that this is a zero-sum game. Okay, so now I want to think about each of these individual terms. Let's think about what we have here now. We're summing up over all of the players of the utility that they could get if they deviated to playing a best response to what their opponents were doing, minus the utility they would get if they didn't deviate. Okay, so this is now their gain, before we had the sum of their utilities if they deviated. Now what we have is the sum of the gains that they get by deviating. Okay. So like, first of all, I claim each of these terms, which individually represents the gain that player I would get if he deviated from playing his part of this, mixed strategy profile to playing his best response to what his opponents are doing. Each of these terms is non-negative. How come?
It's a gain, not a loss.
Yeah, it's like the definition of best response. Like the best response is like what, it's the action that maximizes this expression. So like, you can never deviate to playing your best response and decrease your utility, and it wouldn't have been a best response, right? So it's because AI star was defined to be a best response to these mixed strategies of your opponents. And so, okay, and so what do we have? Well, we've got the sum of a bunch of non-negative terms, and we know that this sum isn't too big. Okay, now it's important and what we want to say is that each of these terms is not too big, right? So like, for each player I, this term is exactly the amount that they can gain by deviating to playing their best response, right? Like what it means for this vector of mixed strategies to be an approximate Nash equilibrium is that this term should be small for every player. Nobody should be able to gain much by deviating. That's what we need to show, that this term is small for every player. Now we know that the sum of these terms is small over all of the players. And if we didn't know that the terms were non-negative, it wouldn't imply that each of the terms was small, right? The sum of the terms could be small because some of them were hugely positive and some of them were hugely negative, right? It doesn't rule out that there's some hugely positive terms. But because each of the terms is also non-negative, if I've got, a million non-negative quantities and they sum up to less than 10, each of them has to be less than 10 because there's no negative numbers out to sort of cancel out large positive numbers. Okay, so this part of the argument is like wasteful, but like if I know that the sum over all of the players of the degree to which they can gain by deviating to playing their best response is at most n times delta t. In particular, I know that there's no player who individually can gain more than n times delta t by playing a best response. Okay, and that's it. If no player can gain individually by more than n times delta t by deviating from their part of this mixed strategy profile to a best response, then by definition, this mixed strategy profile is an n times delta t approximate Nash equilibrium. Okay, that makes sense. So that proves the theorem. Okay, so we now know that in two-player zero-sum games, and actually in this larger class of n-player separable zero-sum games, there's Nash equilibria are sort of easy to find, right? Like in particular, one way to converge to Nash equilibrium is just to have everyone play this very simple polynomial weights algorithm. And that's not the only way. Like the only property we needed about the polynomial weights algorithm was that it was one way to get a sequence of action profiles that had small regret. But like, really, we didn't use any other property of polynomial weights in this argument. This is just a fact about sequence of action profiles that have small regret. Okay, so if you're playing a game with and you find something better to do than polynomial weights, do that. And if it's better in the sense that it only resulted in smaller regret for you, then that's great. Like you've only accelerated convergence to equilibrium. Okay, that's true for everybody. So we now have a not just an algorithmic way of computing Nash equilibria in separable zero-sum games. We've got a plausible dynamic that doesn't require much knowledge of the game, only enough to let you play the polynomial weights algorithm, right? All you need to know is what your loss is for each action on the day that you considered playing it, and you get quick convergence to equilibrium. Okay, so thank you, and see you guys on Tuesday, hopefully in person.
Thank you.
Yeah.
Thank you.
Thank you.